Hello everyone, my name is Bibek. Today I am going to talk briefly about our project titled SteinerLog. SteinerLog automates the process of alert generation as well as correlation in order to detect the ongoing APT campaigns. It utilizes graph traversal and reduction technique to build a concise attack campaign story that can help an analyst with the analysis and response. Just like these existing works, we make use of data provenance graph built on top of system event logs in order to perform threat hunting. Some of the contributions we made in this paper include first utilizing the publicly available IOA repositories and well-known anomaly detection techniques for alert generation, which makes our system much more easier to reproduce. Second, we remove the single point of failure in existing system by replacing their subgraph matching algorithm and graph alignment algorithm with a much more robust measure of correlation, namely Steiner tree optimization. And finally, we were able to scale the alert correlation into hundreds of hosts by utilizing two different granularities of graph and hierarchical exploration. Just like we discussed, we utilize two different granularities of graph in our work. On each of the hosts, we build a per host provenance graph using the operating system level events such as process creation and termination, file manipulation, registry events, and the netflow events. You can see the rough schema of our per host provenance graph on top right of the slide. The direction of each edge represents the direction of information flow between entities. On the network level, we built a user-host interaction graph utilizing the information such as user session logins, RDPs, and remote accesses. This network level graph gives us the visibility into users' movement among multiple hosts. This is the workflow of a SteinerLog system. We start with the CTI repositories compiled by experts and find out the IOA matching rule that are relevant to our system. In addition, we configure the anomaly detector in order to find the events that diverge from the norm. Once we have the provenance graph and list of suspicious events or alert, we perform the price collecting Steiner tree optimization on each host to find the subgraph that are potential representation of attackers' activity. When the threat score of one of such subgraph exceeds given threshold, we extract the metadata from the subgraph such as the users, host, and the time period, and start the exploration on user-host interaction graph. By correlating the movement on user-host interaction graph with the individual subgraphs on different hosts, we can come up with a global attack story. So let's start with the alert generation. Most of the rules for IOA-based detection are compiled from public repositories such as Sigma rules. One thing to note about each of these detection rules is they have one or more MITRE TTP tags associated with them. In addition to the alerts generated by IOA-based matching, we also built the anomaly detector in order to detect events that diverge from the norm but are not detectable by IOA-based signatures. So for anomaly detection, we post profile each of the event types separately. Once we have the behavior profile for different event types, for each of the incoming edge, we compute two scores. First, we determine how rare is given event based on the historical context, and the second is how sparse are the endpoints associated with given edge. So once we have this rarity and sparsity score, we can combine them linearly to come up with an anomaly score. If this anomaly score exceeds a threshold specified by user, then we flag this as an anomaly or an alert. Right, once we have these alerts generated by anomaly detectors and IOA matching and our provenance graph, the next step in the process is to correlate these alerts together into a subgraph that are potential representation of attackers' activity. We formulate this process of alert correlation as price collecting standard tree optimization. For a price collecting algorithm, we need to define two functions. First, the price function, and then the second, cost function. Let's go over each of these functions one by one. Right, so the price function is basically risk score of the subgraph S built on the subset of alerts. So if we have a group of alert that correspond to a subgraph, risk score, the cumulative risk score of all of those alerts is basically our price, and that is what we want to extract. So how do we calculate the risk score of that subgraph? So first of all, each of these IOA matching rules have a severity level assigned to them. For example, informational, low, medium, high, and severe are assigned with the score of 1, 2, 3, 4, and 5 respectively. Similarly, for the alert generated from anomaly detector, we translate the anomaly score, which is between the threshold tau and 1 to the interval 1 to 5. So by combining the score of each of these alert in given subgraph, we can obtain a risk score for given subgraph G, which is the value of price function. Right. So next in line is the definition of cost function, or as we call distance function. So if production of individual alert is an accomplishment for an attacker, the amount of movement it needs to perform between the accomplishment of individual alert is the total cost it has to pay. So we define different distance function in order to measure this cost. The first one is pairwise distance, which basically sums the shortest distance between every pair of alert in given subgraph. While this cost function is great for group of events that are closely related to one another, most of the attack campaign tend to behave like a chain of event rather than group of event. And in the chain of events, the first event and last event can be quite far apart, and the pairwise distance function penalizes that sort of behavior. So we utilize the Steiner distance instead, which is the sum of shortest path distances between adjacent alerts in given Steiner tree, rather than the sum of every pair of alerts. So this inclusion of distance between adjacent alerts only nicely models the chain of event and allows us to capture the actual cost of having to perform an attack campaign. Right, so once we have the price and then the cost associated with our subgraphs, the goal of PCST algorithm is to optimize this discrepancy. We want to extract the subgraph that has maximum price and then the minimum cost. So while this seems really nice and easy, we have a couple of problems in order to apply this directly to our dataset. First, this optimization is an NP-hard problem, and even its approximations are quadratic and cubic in time, and given the size of graph we have with 17 billion events, applying this algorithm on our dataset is computationally impossible. The second problem is this algorithm finds a optimal subgraph, but since we are doing the detection real time, and new events and new information may change what the optimal subgraph is. So in order to accommodate this sort of dynamic environment, we cannot just find the optimal subgraph. Rather, we need to keep eye on all potential subgraphs that may end up being optimal or at least usable. Right, so we did a couple of modification on the PCST algorithm in order to fit the optimization for our problem. So the first is we relaxed the PCST optimization into a local budgeting problem. So instead of maximizing the price and minimizing the distance, we keep track of the price and make sure the distance between adjacent alert in the tree does not exceed a local distance threshold k. So if you have n alert in given Steiner tree, then the total cost bound for given subgraph will be n times k. And then the second is instead of just finding the best subgraph, we maintain all the subgraph that could potentially represent the attacker's activity. And after every time a new alert is inserted or new edge is inserted into the provenance graph, we update all these subgraphs that need to be updated. We merge if the merged subgraph satisfies the local cost bound. So we have bunch of these subgraphs. We keep track of the score for each of these subgraphs, and we also merge them and update them if necessary. So when one of these subgraphs have the risk score that exceeds the user-defined threshold, or if the subgraph is risky enough, then we trigger the cross-host traversal. The way we do it is we basically extract the metadata from the subgraph, such as the user involved, the host in which it was detected, the time period in which the attack was performed, and basically use that information to do the traversal on user host movement graph. Right, so once we have in order to come up with the global attack champion, we need to correlate the attacker activity subgraph on different hosts with the user host movement on network wide graph. Right, so once we have this giant champion subgraph, we're ready to build the concise attack champion graph. Some of the steps involved in this process is, so each of the alert are first translated to the corresponding MITRE attack TTP tags, and then we merge the redundant alert into one single node in that tactical graph. If multiple alerts are produced by same rule, or if the multiple agents or the multiple alert are produced involving same agent or same object, then we merge all of them together into single node for a tactical graph. And then we perform some graph summarization and pruning to only maintain the only necessary edges in the graph. Right, let's move to the evaluation part. We implemented SteinerLog with Python and Elasticsearch like I mentioned earlier. We evaluated the system on operational transparent cyber OpTC data collected by NCR, which is publicly available. It contains 1000 Windows 10 hosts, half of which are shut down during the data collection process. So 500 Windows 10 hosts. In total, we have 17 billion events. Majority of them are file, flow, process, module, thread, and registry event. In total, we have 11 different objects and around 33 different event types. They have 3 different simulated attack champion, one per day. Each of the attack champion touches multiple hosts, impacts multiple users, and we want to see if the SteinerLog can be used to detect the compromised hosts and users. Right, first we want to see if we can detect the compromised hosts and user by using the SteinerLog system. Based on our result, we were able to detect every impacted host and then every impacted users except one on day 1. The one user that we did not detect was compromised on domain controller 1, for which we did not have the log, and hence we were not able to detect it. On day 2, Death Star was particularly noisy and it touched hundreds of different hosts and impacted several users. After performing the temporal correlation with the individual subgraph extracted on different hosts, we were able to prune a lot of false positives, and we did obtain a satisfactory result. Day 3 was more or less straightforward. It only impacted two different hosts, on each of which it performed more or less identical malicious Notepad++ update, and the subgraph corresponding on each of those hosts were scored particularly higher than the rest of the subgraph, and we were able to detect them easily. This slide shows the resource consumption in order to run SteinerLog. The numbers are for per host per day. So we have graphs with 100Ks of nodes and then 2-3 times of that of edges on each host on given day. And for the creation of provenance graph and performing alert correlation, it takes less than a half minute on most of the hosts. So the memory and runtime requirement are well within the reasonable limit. Here we have the risk score associated with different subgraph we have extracted from different hosts during 3 attack campaigns. As you can see, on day 1 host 201 and 660, on day 2 host 501, and on day 3 host 351 and 51 have significantly higher risk score than rest of the subgraph. These hosts and are the one that contains majority of attackers' activity. Some of the compromised user subgraph have a risk score that blends well within those of benign subgraph. That is mostly because attacker leaves very small footprint on some of these machines and move to the next one. We need to perform the temporal correlation between these subgraphs and user host movement graph in order to come up with the decision for these subgraphs. The last task we tested for is the ability of SteinerLog to reconstruct the attack campaign. This slide shows the part of the attack campaign constructed during day 1. It shows the subgraph extracted on host 201 on the left and the user movement on the right. We have similar subgraph extracted on host 660 and 402 and other hosts, which we have not shown here because of the space constraint. Anyway, on host 201 we were able to more or less reconstruct the attacker's steps. That includes malicious file download using Firefox, user execution of downloaded file, then registry installation, then run key installation, and then that the PowerShell performs several discovery techniques, and finally the lateral movement using WMI invoke to host 402. The graph on the right shows the user's movement throughout the network during the attack campaign. The user G-Leaser gets compromised on host 201. It moves to host 402 using WMI invoke, where it elevates to administrator and moves to 660. From 660 it pivots to DC1 and accesses all the credentials and uses them to pivot to multiple hosts afterward. This is the attack campaign reconstructed on host 501 on day 2. Likewise, this is attack campaign reconstructed on host 351 on day 3. Some concluding remarks. We did make some contributions on top of existing work, the major ones being utilization of local constraint PCST to make more robust alert correlation, and utilization of hierarchical traversal in order to scale the system to hundreds of hosts. As far as the future direction goes, we have a couple of direction on mind. The first one is we want to test on more real low and slow APT scenario in contrast to the campaigns we are using on this experiment. Second, we want to utilize the graph learning technique in order to do some proactive filtering and reduce the amount of host that needs this sort of fine-grained analysis. Right, we are at the end of video. I would like to thank all of you for watching it along. If you have any questions, suggestions, or remarks, please feel free to reach out to me on my email address on this slide. Thank you very much.